Hello everyone, how are you doing? Hope they are doing good. I think the concept related to analog circuits, that's over. Now let's go for subject wise test, and this is what is test 1. Okay, let's see the questions. Write down problem number 1. The amplifier circuit shown below uses a composite transistor of a MOSFET and bipolar in cascade. All capacitances are large. GM of MOSFET is 2 milliampere per volt. This is the first problem. Therefore, given GM of MOSFET is equal to 2 milliampere per volt. This is for MOSFET. And HFE is equal to 99. This is for BJT. This is what, then all capacitances are very large. Infinity means very large, and is asking overall transconductance. Therefore, what is overall transconductance for the composite transistor? For the composite transistor. Okay, this is what is the problem. Okay, now let's see the circuit. Circuit is okay. This is what is given, and this is what is our BJT, and this is what is the MOSFET. Okay. Now, therefore, this is what is our composite transistor, right? Now, is asking, when I say this is what is my input voltage and this is what is your output voltage, okay? Asking for this combination, what is effective transconductance or overall transconductance? The GM of MOSFET 2 milliampere per volt, and HFE of your transistor, that is what is 99. Okay. Therefore, now therefore it is a composite transistor. This is what is our composite transistor. Now what is our overall GM? Whatever it may be, if you take a composite transistor, this is what is your composite transistor, and it is defined with what? It is defined with input and defined with output. And it is defined with input and output. What is overall GM? Overall GM, effective GM, right? Therefore, GM effective. That is what is GM effective. I'm just calling it as effective GM is equal to change in output current, change in output current with respect to change in input voltage, change in input voltage when output voltage is constant. We have to keep output voltage constant. See, by saying this, what does it mean? Just remember, I want to know the change in output current only because of input voltage, not because of anything else. Because your circuit will have some output impedance. If it is having output impedance, if you change your output voltage, your output current also will change. Similarly, your output current is also controlled by input voltage. Therefore, but I want to know only output current change because of input voltage change only. Therefore, I am keeping my output voltage constant such that the change in output current is only because of change in input voltage. That is what your transfer or transconductance, output current to input voltage. Okay, that is fine. Therefore, now tell me, if you take this as your, what do you call, effective composite transistor, then tell me what is your output current. First of all, this is what your collector current. Can I say collector current is nothing but your output current? This is what your collector current IC. I am representing DC, but I'll say delta IC, what it may be. Then this is what your input voltage. Therefore, what is your input voltage? Input voltage is nothing but VGS. This is what your VGS. Okay. Therefore, now if you see here, what is GM effective from this? GM effective is nothing but change in output current, that is nothing but delta IC. IC is DC current, but GM is AC parameter. Therefore, I want to know the change in IC. What is the reason to have change in IC? Change in VGS. Change in VGS is nothing but your AC signal what you are applying. Because of AC signal, what is the change in VGS? Capital VGS is because of biasing. The change in VGS is because of external input AC signal, which is what is applied on top of the DC signal, which is from R1 and R2 of your biasing circuit. Therefore, I want to know the change in VGS is giving some change in IC. Therefore, what is that when you keep output constant? What it may be. Therefore, what is change in VGS? This is what people call it as what? This is what people call it as small IC divided by small VGS. When output voltage is constant, your capital V0 is constant. Or like I say, if I speak everything, right? Okay, that's fine. Capital V0 is constant. Or your delta V0 is 0. When you say output voltage is constant, that is a constant value, then what is change in value? Change in value is 0. That's what people say, IC by VGS, when your small V0 is equal to 0. Change in V0 is represented with small V0. Okay. Therefore, this is what, if I say this is what is given, let us say AC signal only small V0. Therefore, now tell me, can I write this as, what is our IC? Can I write it as IC divided by IE and IE divided by VGS? When small V0 is equal to 0 means output constant. Therefore, what is your V0? VCE of transistor, BJT plus VDS of your transistor. Let us say there is no change, then this is also constant, this is also constant. Therefore, the change in VCE is 0, change in VDS is 0. Then what is your IE? What is IC by IE? IC by IE. Right? If you neglect reverse saturation current, IC by IE. Right? That is nothing but what? IC is equal to, we know, right? We know that IC is equal to capital IC. Okay, that's fine. Alpha into IE or IC is equal to what? Beta into small ib. What is beta? Beta AC. What is beta AC? Beta AC is nothing but HFE. Therefore, HFE into IB. Therefore, what is IC by IE? IC by IE is nothing but alpha. And I gave the relationship between alpha and beta. Therefore, what is alpha? Therefore, we know that alpha is equal to beta divided by 1 plus beta. Okay. Therefore, IC by IE is nothing but your alpha. Therefore, alpha is nothing but IC divided by IE. Okay, what is your beta? Beta is nothing but IC divided by IB. We know all these things, right? Beta is nothing but HFE. Beta AC is nothing but HFE. Okay, beta AC is nothing but, and this is alpha AC. This is alpha AC. This is nothing but your HFB. Okay, that's fine. Whatever may be. Therefore, IC by IE is nothing but your This is what is your alpha. But what is IE? The emitter current is nothing but your drain current. Can I say this is what your ID? But that is nothing but your IE also. Therefore, the same current is coming. This is ID and the same current is also. Therefore, what is this current? This is nothing but your IE. IE is nothing but your ID only, right? Therefore, change in IE is nothing but change in ID. Alpha into small ID divided by small VGS. When V0 is constant means when VDS is also constant. Then what is your alpha? Alpha is known to you beta by beta divided by 1 plus beta. And what is ID by VGS? That is nothing but GM. This is nothing but your GM. Therefore, what is GM effective? GM effective is equal to beta is nothing but HFE. HFE divided by 1 plus HFE into GM. Therefore, what is HFE? Given 99 divided by 100 into 2 milliampere per volt. Therefore, which is nothing but 0.99 into 2 milliampere per volt, which is nothing but 1.98 milliampere per volt. Strictly speaking, your GM effective is approximately equal to the GM of your MOSFET. That you can say. Okay, that's fine. Basically, this is nothing but your because two different types of transistors. This is common source amplifier, applying input voltage at the gate with respect to source, taking output at drain with respect to source. This is common source, but this is nothing but common base, applying input at emitter with respect to, for AC analysis. This is shorted, right? Therefore, this is nothing but reference or ground. Therefore, base is common, applying your output voltage at collector with respect to base, which is the reference. Therefore, for both input and output, base is common. This is common base configuration and this is common source configuration. Therefore, what is this? If instead of MOSFET, if it is BJT, then it is common emitter, common base, it is cascode amplifier. That's why it is specified that it is cascode amplifier. Okay. I think answer is over. What is the answer? Answer is D. Answer is D. Your GM effective is approximately equal to GM. If you want, you can say like that also. Take it. After this, we will solve problem number 2. I'll give you 1 minute time. Then after that, we will see problem number 2. Actually, small VGS is nothing but your V in, small signal AC voltage. small Vin, okay. The small Vin will be imposed on top of capital VGS. Capital VGS is set by the biasing circuit. That is DC analysis and then AC signal on top of it. Done? Now, problem number 2. In figure, all transistors are identical. And have a high value of beta. High value of beta. Infinity means not infinity, very high. The voltage VDC is equal to, okay, circuit is, this is 5 milliampere. This is diode connected BJT. Therefore, what is that VDC? Okay. Now, I think we solved one problem which is related to current mirror. Okay. What is current mirror? If you take a current mirror, typical current mirror, this is cascade current mirror. If you take current mirror from BJT or MOSFET, anything is fine. Therefore, if you see that this is what is your current, this is what is called I bias, and this is what is your diode connected BJT or MOSFET. You can replace your BJT with MOSFET. Both are almost same. And this is what is our load. This is what is your BCC. And let us say this is what is your RC. Okay. Now this is what is transistor Q1 and transistor Q2. You remember, I think we solved one problem where, let us say beta is very high and beta is very high. The meaning of beta very high is nothing but, if you take your IE is equal to IC plus IB, right? Therefore, your IC plus IC by beta. If beta is very high, you can neglect IB, right? If beta is very high, the meaning of saying beta is very high is nothing but your IB can be neglected. IB can be neglected with respect to IC or IE. Okay, that is the meaning of it. It's not zero. It's not zero. Can be neglected with respect to IC. If IB is there stand alone, we cannot say zero. If IB is there along with IC, then we can neglect IB. That is the meaning of it. With reference to IC, we can neglect IB. Reference is very important. Now, this is what is current mirror. Why it is current mirror? I already explained. Whatever VBE, see, this is an active region, provided we have chosen RC such that it is also an active region. How will you know that both are in active region? If VCE is greater than 0.2, VCE2 is greater than 0.2, both are in active region. And here what is VCE? VCE is nothing but VBE only. Your VBE of this transistor, this is nothing but your VBE1 and this is VBE2. Surely, according to KVL, VBE1 is equal to VBE2. Whatever voltage you have, the same voltage we have. Let us say both are having same beta. If both are having same beta, then both are having same VBE, both are in active region, then both will have same collector current. Actually, whatever I bias is nothing but this current is equal to this current plus this current. What is this current? Actually, this is nothing but, let us say this is what is your IC1, and what is this current? This is nothing but IB1 plus IB2. Therefore, this is IB1 plus IB2. But you can neglect it, approximately equal to 0. Why? Because your beta is very large, you can neglect IB1, IB2 with respect to IC. If this is what is the case, then what is your IC1? IC1 is nothing but I bias, right? Therefore, what is your IC1? Therefore, your IC1 is equal to I bias. Whatever bias current you have from your current source, that is what it is. And we know that this Q1 is having VBE1, the same VBE1 is given, both are in active region, therefore, surely same IB1, therefore IB1 is equal to IB2, let us say, IB1 is equal to IB2, both are identical because both are having same VBE, then both will have same beta, then both will have same collector current. What is IC1? I bias. What is IC2? Your IC2 will be equal to I bias only. Your IC2 is equal to I bias, provided beta 1 is equal to beta 2. Therefore, your IC2 is equal to I bias. Since beta 1 is equal to beta 2, both are identical. Okay. Let us say beta 1 is equal to beta 2. Okay. But this is having twice the area of Q1. Then remember, twice the area means the area of cross section of Q2 is twice with respect to Q1, then your current will be twice of your collector current 1. But let us say all are identical. If all are identical, then IC2 is equal to I bias. Therefore, what is this? This is what is called current mirror. Whatever current you have in this branch, the same current is coming to the second branch, therefore it is mirrored. That's why this is what is called current mirror. Actually, that is what we have here. Whatever current you have here, the same current will flow here. The same current is flowing here. Again, there is another current mirror, back-to-back current mirror. Therefore, whatever current is flowing here, the same current is flowing here. This is to increase, or this is to avoid higher order effects. That is the reason why they are in what we call in series. If they are in series, it will decrease the channel length modulation effect or base width modulation effect of your transistor. Here it is BJT, therefore base width modulation. That is fine. Therefore, whatever current you have here, the same current is flowing here. Whatever current you are having, the same current is flowing here, which is true. 5 milliampere, 5 milliampere. Then what is your VDC? Therefore, output KVL. Because what is your output current? Now your output current is nothing but same thing. If all are identical, that is very important. Therefore, what is this current now? Same current is flowing because this is current mirror. Therefore, now tell me what is your output KVL? 10 is equal to 5 milliampere into 1K plus VDC. Therefore, this voltage is equal to this voltage plus this voltage. Therefore, what is VDC? Your VDC is equal to 10 minus 5, 5 volt. Therefore, what is the answer? 5 volt. Maybe for your check, what is VC of this? VC of this is nothing but VBE. What is VBE? 0.7. Out of 5, 0.7 is gone here. That is nothing but 0.7. Remaining 4.3 will be coming to this transistor. 4.3. Therefore, this is what is in active region. Okay, fine. Take it. Therefore, answer is 5 volt. This is also current mirror. And it is specified clearly in figure, all transistors are identical and high value of beta. High value of beta is indicating you can neglect base currents with respect to collector current, means whatever bias current which is what is flowing from coming from your bias or your current source, that will be directly flowing into collector current, which you can where you can neglect the base currents, and all are identical, then same current will be flowing. Okay, I'll give you 30 seconds time. Then we will see problem number 3. This is straightforward. I think multiple times we had seen this, right? Problem number 3. The people who solved it, you can go for problem number 3. Done? Okay. Problem number 3. A cascade amplifier stage is equivalent to common emitter stage followed by common base stage. That is the answer. Common base stage followed by common emitter amplifier? No. Therefore, what is that? Your cascade amplifier or cascade structure is nothing but common emitter amplifier followed by common base. This is the answer. Therefore, what is the answer? Answer is A. We have seen this, right? This is what is the name. The name of cascade is nothing but common emitter plus common base. If you ask me in the case of MOSFET, this is in the case of what? In the case of BJT. Now in the case of MOSFET, what is that cascade? Common source plus common gate. This is what is your, this is also called cascade only. This is MOSFET. I already told, right? Because if you take your BJT collector, emitter, base, and if you take your MOSFET, drain, source, gate. When you say common emitter, common source. When you say common emitter, here common source. When you say common collector, this is common drain. When you say common base, this is nothing but common gate. When you say CE with RE, CE with RE, here this is nothing but CS with RS. Here when you say CC emitter follower, here source follower, all. That's why CE, CS, CB, common base, common gate. That is what is with respect to MOSFET. Okay. That is what is problem number 3. Now problem number 4. What is problem number 4? Therefore, what is the answer? Answer is A for that. Okay. Problem number 4. The current gain of a BJT. Current gain of a BJT. Current gain of a BJT. He has given multiple options. Let us say option A, GM into R naught. This is voltage gain, not current gain. GM by R naught. GM into R pi. Option D, GM divided by R pi. See, the R pi is nothing but your resistance, input resistance from hybrid pi model. Okay, that is fine. Now, if you take your BJT, right, this is your collector, emitter, base. Okay, let me say IC, capital IC, and this is what is capital IB. But current gain is defined as what? Not DC current gain, AC current gain. Therefore, current gain is defined as delta IC divided by delta IB when your VCE is constant. Okay. Actually, this condition is important, but even though you don't bother about it, but it is required VCE to be constant. What is change in IC? Only because of IB. That is what is your current gain. Because your IC can be changed using VCE also. You consider phase width modulation, right? That's why to do not see all those effects, I want to see the change in IC because of only change in IB. It's like transconductance, but this is current gain. Therefore, keeping VCE constant, if you keep VCE constant, whatever change you have in the conductor current, that is because of only IB. That is what your current gain. Okay, that is what is your small IC divided by small VBE. This is nothing but your small IC divided by small IB, because what is small IC? Delta IC is nothing but small IC. That is what we represent when delta VCE is 0 or small VCE is 0. There is no change basically. There is no change. Now we know, right? What is this? This is nothing but your current gain. What is your current gain? Therefore, can I write your IC is because of IB, then IB is because of VBE. I can write in a different way also, right? How can I write? Therefore, which we can write like this: IC divided by VBE, then VBE divided by IB, keeping VCE constant. That is there always. What is IC by VBE? IC divided by VBE is nothing but output current divided by input voltage when VCE is 0. When your VCE is 0, then this is nothing but your transconductance, GM, right, into what is VBE by IB? The input impedance. What is input impedance? If you take hybrid pi model, the input impedance is, you can say, R pi. Therefore, what is your current gain? GM into R pi. Strictly speaking, current gain is nothing but your HFE. Therefore, HFE is equal to GM divided by HIE. We already, what is HFE? Current gain. What is GM? Fine, sorry. GM into HIE. GM into HIE. What is HIE? If you take H parameter model, this is from hybrid pi model. Therefore, this is from hybrid pi model. But if you take H parameter model, from H parameter model, what is your HFE? HFE is equal to GM into HIE. But from hybrid pi model, what is your current gain? This is what your current gain. Therefore, that is nothing but GM into R pi. Therefore, what is the answer? Answer is C. Your R pi is nothing but input impedance, input resistance from hybrid pi model. This is transconductance. Therefore, answer is C. Now, fifth problem. Fifth problem is generally the gain of a transistor amplifier falls at high frequency due to. Therefore, if you consider RC coupled CE amplifier, that is what it refers to. RC coupled CE amplifier. Right? If you take, these are all coupling capacitors. Okay, CE, CC, CB. If you take frequency response of this amplifier, we had seen already. Okay, your low frequency gain is limited by your coupling capacitors, and your high frequency gain is limited by your BJT internal capacitances. That is nothing but this cap and the Meller cap what you have, right? Therefore, because of this is nothing but your diffusion capacitance, and this is what your transition capacitance. Okay. Therefore, your high frequency response is limited by this is what. Therefore, this is what is your mod AV. Now, therefore, this is limited by due to coupling capacitors. Coupling capacitors, and this is due to BJT internal capacitances, BJT internal parasitic capacitances, internal parasitic capacitance. Parasite is nothing but unwanted parasitic capacitances. That is because of PN junction diodes. Okay. So tell me what is the answer? Generally, the gain of a transistor amplifier falls at high frequency due to option A, internal capacitance of the device. Yes, that is true. Option B, coupling capacitor at the input. This is because of this coupling capacitor, your low frequency response is limited, not high frequency response. Skin effect. Skin effect is due to very high frequency. That is only for resistance part. And D, coupling capacitor at the output. No. Therefore, your high frequency response fall is because of internal capacitances. Therefore, what is the answer? Answer is A. For the fifth one, answer is A. Okay. Now let's see sixth problem. What is sixth problem? The Ft of a BJT is related to its GM, C pi and C mu as follows. Actually C pi and then C mu is nothing but CD only, and C pi is nothing but your CT only, whatever it may be. Okay. Therefore, if you take your BJT, this is what your BJT. This is collector, emitter, and then base. What is Ft? Ft is defined as, this is nothing but transition frequency. Transition frequency. Okay. What is the definition of Ft? Right? The definition of Ft, if you treat this as a black box, okay, this is what your output and this is what your input, where emitter is common for both input and output, like common emitter configuration. Transition frequency is nothing but the frequency at which Ft is nothing but the frequency at which the short circuit current gain. The short circuit, I'll explain what is this. The short circuit current gain. Short circuit current gain of BJT, of a BJT is equal to 1. For what frequency your input AC current is equal to output AC current. That is what your Ft. But what is the meaning of short circuit? Means the current gain is nothing but what? Change in output current only because of change in input current. Then we have to take capital VC 0, delta VC 0. That is nothing but short circuit. When you short collector and emitter, whatever output current you have, if that output current is equal to input base current. But is it true? Typically, what is current gain? Just before, I think fourth problem we defined. What is current gain? Change in output current only because of change in input current when VCE is equal to constant or delta VCE is equal to 0. Then definitely that is nothing but your beta or HFE, right? But now, how can you say the short circuit current gain? Short circuit is nothing but again VCE is 0. Therefore, how can you say the short circuit current gain is equal to 1? Yes. Why short circuit current gain will be 1? When input current is equal to output current. When that will happen? When very high frequency, at very high frequency, the capacitances what you have, right? The BJT internal capacitances whatever you are having, right? They are like short circuit. That your input current will be equal to your output current. Therefore, whatever current you are getting, right? Whatever current you are going to get. Therefore, if you take only BJT part, okay? Whatever current you are getting, right? Then that current will be equal to your base current. The frequency at which that current is equal to base current. That is because of BJT internal capacitances. Okay. Now, if you take hybrid pi model, what is hybrid pi model? This is what is having. Okay. Now, this is what your input resistance. This is what? R pi. I think by this time you should understand. Actually, if you take H parameter model, that is HIE. But now it is R pi. Then output side, HFE into IB in H parameter model. But in the case of hybrid pi model, this is nothing but GM into VBE. This is what is our VBE. And your base to emitter, we have a capacitor. What capacitor? We have what? We have a PN junction diode. Therefore, we have diffusion capacitance, but people call that as C mu also. Instead of CD, that is also called as diffusion capacitance, C mu. Therefore, that we have here, that is what we are having. This is what is our C mu. Then output side, if you include channel length base width modulation, we have this is what is our collector to emitter. This is what is your base, and this is your emitter, and this is what is your collector, and this is your emitter. This is RCE. You can say your R naught or 1 by HOE, whatever you represented. And there is another cap, because this is nothing but your PN junction diode, reverse bias PN junction diode. We have another cap between collector to base to collector. That is what your CT, but people call it as C pi, because that is what is acting as a pi bridge. And it is a reverse bias PN junction diode. That also people represent some resistance, right? That is to have feedback from VCE to IB. Therefore, this is what people added. This is what is RBC, because of base width modulation, and there is a cap. This is what is our C pi. This is what is C pi. This is like what? This is like, and this is what your VCE. This is what your VCE, and this is what your collector current IC, small IC, and this is what your base current, small IB. Now what you need to do, you need to calculate the current gain, short circuit current gain. Therefore, if you calculate short circuit current gain AI is equal to what is our IC with respect to IB, the transfer function, when your small VCE is equal to 0. If you calculate the short circuit current gain, that you can calculate using KCL, KVL. You treat like Z1, Z2, Z3, then try to calculate. It is simply finding the transfer function. Once you know the transfer function, right, the frequency at which your current gain is equal to 1 means the frequency at which your AI is equal to 1. Short circuit AI. Short circuit is indicating this. This is nothing but short circuit. Okay. Short circuit AI is equal to 1 is nothing but your FT. If you calculate, what you get, that FT is equal to GM divided by 2 pi into C pi CD plus CT. Okay. C pi plus your C mu plus C pi. This is what is FT. Therefore, what is the answer? GM by 2 pi into C plus this thing. This is what your FT. This is what is indicating the maximum speed what your BJT can have. This is what is called, you can call it as unity gain frequency, but unity current gain frequency. Okay, this is what your FT. Therefore, what is the answer? Your answer is D. Answer is D. Okay, take it. FT is nothing but short circuit current gain. The frequency at which the short circuit current gain. What is short circuit current gain? When VC is equal to 0, output current divided by input current, you try to find the transfer function using nodal analysis or whatever it may be. Then you'll get in terms of S, because there is a capacitor, right? C pi, then C, then 1 by SC, 1 by S, C pi you'll get. Then S is equal to J omega, the frequency at which the total magnitude, right? Mod AI. The short circuit current gain, actually mod AI is equal to 1. That is what is your FT. If you calculate from the transfer function, you will get GM by 2 pi into C pi plus C mu, or CD plus CT. CD is diffusion capacitance, CT is transistor capacitance. Okay. I will give you 30 seconds more. Then we will see problem number 7. Therefore, if you can try to compare, R pi is nothing but HIE in the case of H parameter model, and RCE is almost correlated to 1 by HOE, GMVBE, but it is not straightforward, related to HFE. That's why you got right. HFE, GM is equal to HFE into HIE. Therefore, GM to H parameters. We already correlated before. Okay. Done. Now, problem number 7. What is problem number 7? In a multi-stage RC coupled amplifier, the coupling capacitor, this is single stage. If you take multi-stage, multiple stages. The coupling capacitor, what is coupling capacitor? This is coupling capacitor, this is also coupling capacitor, this is also coupling capacitor. Yes, the coupling capacitor. Option A, limits the low frequency response. Yes, because of your coupling capacitors only, your low frequency response is limited. Limits the high frequency response? No. Does not affect the frequency response? Surely it will affect frequency response. Blocks the DC components without affecting the frequency response. Yes, it will block the DC component, but it will affect frequency response also. But saying D. Therefore, what is the answer? Answer is A. For the 7th one is related to almost 5th one. Therefore, 7th one is nothing but answer A. These are all straightforward. Whenever you get qualitative problems, right? The advantage of qualitative problem is we can get the answer immediately. The disadvantage of qualitative problem is if you don't know the answer, we cannot get it. But if it is related to mathematical analysis, if you try to solve something, if you invest more and more time, you'll get the answer. But qualitative problems, if you don't know the concept, we cannot solve the problems at all. Over, right? Okay. Now, write down problem number 8 and 9. Actually, this is linked answer problem. Okay. Linked answer problem. Consider the CMOS circuit shown. This is linked answer problem 8 and 9. Linked answer problem. For the second bit, first bit answer is required. Okay. 8 and 9. What is the data given? Consider the CMOS circuit shown where the gate voltage VG of NMOS is increased from 0 while the gate voltage of PMOS is kept constant at 3 volt. Assume that for both the transistors the magnitude of the threshold is 1 volt and the product of the transconductance parameters and the W by L ratio, that means mu and C of W by L is 1 milliampere per volt square. Therefore, given Vt of your NMOS is equal to mod Vtp of PMOS is equal to 1 volt and mu into Cox into W by L for both NMOS and PMOS is equal to 1 milliampere per volt square. This is what is given, and the circuit is, this is what is the circuit. Your PMOS gate is connected to 3 volt, that is kept constant, and then power supply is V 5 volt. Therefore, the VGS of PMOS is constant. But the input is what? VG. This is what is, we are increasing from 0 to power supply. This is the variable. Now, this is what is your V0. This is what is the circuit. Okay. Now, what is eighth problem? If you see the eighth problem, what is eighth problem? Eighth problem is problem number 8. For small increase in Vg beyond 1 volt, when Vg increases, when Vg is greater than or equal to 1 volt, small increase in Vg beyond 1 volt, which of the following gives the correct description of the region of each MOSFET? Asking for what is region of each MOSFET. Okay, this is NMOS and this is what is our PMOS. N MOSFET or P MOSFET, anything is fine. Asking when Vg is slightly greater than 1 volt, what is the region of the transistor? That is what is the problem. Okay, just listen. See, for example, ultimately we want to know, therefore, what is the region of the MOSFET? Tell me, point 1, when Vg is equal to 0, when Vg is equal to 0, when Vg is equal to 0, what about your NMOS? For NMOS, what is your VGS? Your VGS is equal to 0, therefore cut off. Therefore cut off. But if you take PMOS, right, what is your mod VGS? Your mod VGS is nothing but 3 volt minus 5 volt, that is 2 volt. Okay, then when it is cut off, right, when this is what is cut off, this is open. When this is open, then definitely your PMOS is on. When PMOS is on, your V0 will be 5 volt, then your mod VDS will be 0. When mod VDS is 0 means this is in linear region. Therefore, if you ask me, your PMOS is on with on resistance, your NMOS is off, therefore this is what your 5 volt, this is what is your R on of P, and this is what is your V0. What is your V0? Your V0 is equal to 5 volt. That is what we get it. Therefore, it is nothing but linear region. Now the problem is not with Vg is equal to 0. Now the problem is when as Vg is increasing, let us say when Vg is greater than or equal to 1 volt. Now we need to find. Okay. Time is almost over. We will continue in the next session. In the meantime, you try to think about it. Thank you.